Sklearn tree. Description. Decision trees are a powerful machine learning algorithm used for both classification and regression tasks. They create a tree-like structure where each internal node represents a feature or attribute of a data, and each branch represents a possible value of that feature. The tree is constructed in a top-down manner by recursively partitioning the data based on the most informative features. This process continues until the leaves of the tree are reached, which represent the final predictions. Inputs. Feature matrix: a dataset containing numerical and categorical features. Each row represents an instance, and each column represents a feature. Target variable: the variable that the model aims to predict. For classification tasks, this is a categorical variable, while for regression tasks, it is a continuous variable. Outputs. Prediction: the predicted value for the target variable for a given input. Decision tree model: the trained decision tree structure, which can be used to make predictions on new data. Steps. Data preparation: this involves cleaning and pre-processing the data, including handling missing values, transforming categorical features, and scaling numerical features. Tree construction: the algorithm recursively splits the data into subsets based on the feature that best separates the instances into different classes or values of the target variable. This process continues until the leaves of the tree are reached, which represent the final predictions. Pruning: to prevent overfitting. The tree is often pruned by removing branches that do not improve the model's performance on a validation set. Metrics. Accuracy: for classification tasks, this measures the proportion of correctly classified instances. Precision: this measures the proportion of positive predictions that were actually positive. Recall: this measures the proportion of positive instances that were correctly identified as positive. F1 score: this is the harmonic mean of precision and recall. Mean squared error (MSE) for regression tasks. This measures the average squared difference between the predicted and actual values. R squared for regression tasks. This measures the proportion of the variance in the target variable that is explained by the model. Visualization plots. Decision tree diagram: this visualizes the decision tree structure, showing the features, splits, and predictions at each node. Feature importance plot: this shows the relative importance of each feature in the decision tree. Fine-tune parameters. Max depth controls the maximum depth of the tree, limiting the complexity of the model to prevent overfitting. Minsample split specifies the minimum number of samples required to split an internal node. Minsample's leaf specifies the minimum number of samples required to be at a leaf node. Criterion defines the splitting criteria. Common options include Gini for the Gini impurity, which measures the probability of misclassifying a randomly chosen instance, and entropy for information gain, which measures the reduction in uncertainty after a split. Uncertainty methods. Confidence interval: the prediction interval provides a range of values that are likely to contain the true value of the target variable. Out-of-bag error for random forest models, which are ensembles of decision trees. This is an estimate of the model's error based on the data that was not used to train each individual tree. Challenges and fixes. Overfitting. Sample use case that resulted in challenge 1: a decision tree trained on a dataset with a small number of instances may overfit to the training data, leading to poor performance on unseen data. Fixes to challenge 1. Use techniques like pruning or regularization to prevent the tree from becoming too complex. Use cross-validation to evaluate the model's performance on unseen data. Sensitivity to noise. Sample use case that resulted in challenge 2: decision trees can be sensitive to noisy data. where outliers or irrelevant features can significantly impact the tree structure. Fixes to challenge 2. Clean the data to remove noise and outliers. Use feature selection techniques to identify and remove irrelevant features. Interpretability. Sample use case that resulted in challenge 3. Very deep and complex decision trees can be difficult to interpret, making it challenging to understand how the model arrives at its predictions. Fixes to challenge 3. Use visualization techniques to help understand the tree structure. Limit the depth of the tree to make it more interpretable. Data imbalance. Sample use case that resulted in challenge 4. If the data is imbalanced, meaning that one class is significantly more frequent than others, the decision tree may favor the majority class and perform poorly on the minority class. Fixes to challenge 4. Use techniques like oversampling or undersampling to balance the data. Use metrics like F1 score or AUC to evaluate the model's performance on both classes. sklearn. Tree. Decision tree classifier. Description. The decision tree classifier is a supervised learning algorithm used for classification tasks. It builds a decision tree based on the features of the training data, aiming to predict the class label of new, unseen data. The tree is constructed by recursively partitioning the data into subsets based on the values of features. At each node, the algorithm selects the feature that best splits the data into distinct classes, using criteria like Gini impurity or entropy. The process continues until a predefined stopping condition is met, such as reaching a maximum depth or a minimum number of samples in a node. Once the tree is built, predictions are made by traversing the tree from the root node to a leaf node, following the feature splits based on the values of the input data. Inputs. X the training data, which is a 2D array of shape n samples. N features where each row represents a sample and each column represents a feature. Y the target labels corresponding to the training data, which is a 1D array of shape n samples, containing the class labels for each sample. Outputs. The trained decision tree classifier object. Predictions for new data when provided with unseen data. The classifier can generate predictions, which are the predicted class labels for the input data points. Steps. Training. The algorithm learns from the training data to build a decision tree structure. Prediction. Given new data, it traverses the tree based on the feature values, reaching a leaf node that represents the predicted class. Metrics. Accuracy measures the proportion of correctly classified samples. Precision measures the proportion of correctly predicted positive samples among all predicted positive samples. Recall measures the proportion of correctly predicted positive samples among all actual positive samples. F1 score. A harmonic mean of precision and recall, providing a balanced metric for imbalanced datasets. Entropy measures the impurity of a node, reflecting the uncertainty of class labels within the node. Gini impurity measures the probability of misclassifying a randomly chosen sample from a node. Visualization plots. Tree plot visualizes the decision tree structure, showing the features used at each split and the resulting class labels. Feature importance plot shows the importance of each feature in the decision tree model, indicating which features are most influential in predicting the class label. Fine-tune parameters. Criterion. The splitting criterion used to determine the best split at each node. Options include Gini impurity or entropy information gain. Max depth. The maximum depth of the tree, limiting the complexity of the model and preventing overfitting. Min samples split. The minimum number of samples required to split an internal node. preventing the creation of very small nodes that might lead to overfitting. MinSamples leaf: the minimum number of samples required to be at a leaf node, ensuring that leaf nodes are not too small and represent a sufficient amount of data. Max features: the maximum number of features considered at each split, limiting the number of features evaluated and potentially reducing computational cost. Uncertainty methods. Confidence: the probability of the predicted class label can be used to quantify the certainty of the prediction. Higher probabilities indicate higher confidence. Entropy: the entropy of the leaf node can be used to measure the uncertainty in the prediction. Lower entropy values indicate lower uncertainty. Challenges and fixes. Challenge 1: overfitting: the decision tree may overfit the training data, leading to poor performance on unseen data. Sample use case training: a decision tree on a small dataset with a high number of features might result in a complex tree that captures noise in the data. Fixes. Reduce tree complexity using parameters like max depth, MinSamples split, MinSamples leaf, or max features can help limit the tree's complexity and prevent overfitting. Regularization techniques like pruning or using a penalty on the number of leaves can help regularize the model and improve generalization. Cross-validation: using techniques like cross-validation during training can help evaluate the model's performance on unseen data and identify potential overfitting. Challenge 2: handling missing values: the decision tree algorithm can handle missing values by either ignoring the feature or using a surrogate split. Sample use case data with missing values might lead to biased splits or inaccurate predictions if not handled properly. Fixes. Imputation: replace missing values with imputed values based on the distribution of the feature or other related features. Ignoring the feature: ignore the feature entirely during training if it has too many missing values. Surrogate splits: use surrogate splits to find alternative features that can be used to split the data when the primary feature has missing values. Challenge 3: handling categorical features: decision trees can handle categorical features by converting them into numerical values using one-hot encoding or other techniques. Sample use case: categorical features with many levels might lead to a large number of splits in the tree, potentially increasing complexity. Fixes. One-hot encoding: convert each category into a binary feature, creating a separate feature for each category. Ordinal encoding: assign numerical values to categories based on their order or importance. Feature engineering: combine categorical features or create new features from them to improve model performance. Challenge 4: interpretability: decision trees can be easily interpreted, but understanding the reasoning behind complex trees can be challenging. Sample use case: a very deep tree with many splits can be difficult to understand and interpret. Fixes. Visualization: use tree plots and feature importance plots to visualize the decision tree and understand its structure. Partial dependence plots visualize the relationship between a single feature and the predicted output, providing insights into the feature's influence. SHAP values explain the impact of each feature on a specific prediction, providing insights into the contribution of each feature to the decision. sklearn. Tree. Decision tree regressor. Description: decision tree regressor is a supervised learning algorithm used for regression tasks in machine learning. It builds a tree-like structure where each internal node represents a feature. Each branch represents a decision rule based on that feature. And each leaf node represents a prediction for the target variable. The model learns from data by recursively partitioning the feature space based on the best split points that minimize the prediction error. Inputs: X, the training data containing the features used to predict the target variable. It should be a 2D array or a pandas data frame. Y, the target variable values for the training data. It should be a 1D array or a pandas series. Outputs: Predictions, the predicted values for the target variable for new unseen data. These are obtained by traversing the decision tree from the root to a leaf node based on feature values of the new data. Decision tree model: a trained decision tree regressor object that can be used to make predictions and analyze the decision-making process. Steps: Data preprocessing: the input data is typically preprocessed to handle missing values, outliers, and to scale or normalize features. Tree construction: the decision tree is built recursively. At each node, the algorithm iterates through all features and selects the one that results in the best split, based on a chosen impurity measure like mean squared error (MSE) for regression. Pruning: to prevent overfitting. The decision tree might be pruned after construction by removing branches that do not significantly improve the prediction accuracy. Metrics: mean squared error (MSE) measures the average squared difference between the predicted and actual target values. Lower MSE indicates better model performance. R-squared R2 measures the proportion of the variance in the target variable that is explained by the model. Higher R2 indicates better model performance. Visualization plots. Decision tree visualization: the decision tree structure can be visualized as a graph showing feature splits, branches, and leaf nodes. This helps understand the model's decision-making logic. Fine-tune parameters. Criterion defines the impurity measure used to evaluate the quality of splits, e.g. MSE for mean squared error. Max depth limits the maximum depth of the tree to prevent overfitting. Minsamples split: the minimum number of samples required to split an internal node. Minsamples leaf: the minimum number of samples required to be at a leaf node. Max features: the number of features considered for splitting at each node. Uncertainty methods. Bootstrap aggregating bagging: multiple decision trees are trained on different subsets of training data and their predictions are averaged to reduce variance and improve the models. Robustness. Challenges and fixes. Challenge 1: overfitting: when the decision tree is too complex. It might perfectly fit the training data but generalize poorly to unseen data. Sample use case that resulted in challenge 1: a decision tree with a large depth might capture noise in the training data, leading to overfitting. Fixes to challenge 1: reduce the tree's depth using the max depth parameter. Increase the minsamples split and minsamples leaf parameters to prevent splits on small subsets of data. Apply pruning techniques to remove unnecessary branches. Challenge 2: sensitivity to noise: decision trees can be sensitive to outliers and noisy data points. Sample use case that resulted in challenge 2: a few outliers in the training data might significantly influence the split points, leading to poor generalization. Fixes to challenge 2: preprocess the data to handle outliers, such as removing them or transforming them using robust methods. Consider using ensemble methods like random forests, which train multiple trees on different subsets of data and average their predictions, reducing the impact of outliers. sklearn. Tree. Extra tree classifier. Description. Extra trees classifier is an ensemble learning method for classification that operates by constructing a multitude of decision trees during training and outputting the class that is the mode of the class is classification or mean average prediction regression of the individual trees. The trees are built in a completely randomized way, meaning that at each node, a random subset of features is chosen from the total set of features, and the best split among the chosen features is selected. This randomization process leads to a high degree of diversity among the trees, reducing the risk of overfitting and improving the model's generalization ability. Inputs. X. This input represents the training data, typically a 2D array of shape n samples. N features. Each row represents a data point, and each column represents a feature. Y. This input corresponds to the target variable, a 1D array of shape n samples, containing the class labels for each data point in X. Outputs. Fitted model. After training, the extra trees classifier model learns a set of decision trees that can be used to predict class labels for new, unseen data. Predicted class labels for a given input dataset X. The model outputs predicted class labels for each data point. Steps. Tree construction. The algorithm creates a specified number of decision trees. Each tree is built on a random subset of the training data and a random subset of features. Splitting criteria. At each node, a random subset of features is selected. Then, the best split among the chosen features is determined based on a criterion like Gini impurity or entropy, aiming to maximize information gain. The split is chosen randomly among the best splits, introducing further randomness. Prediction. To make a prediction for a new data point, the model passes it through all the decision trees. The output of each tree is the predicted class label. The final prediction is determined by the majority vote most common class label among the trees. Metrics. Accuracy. This metric measures the proportion of correctly classified instances. It's calculated as the number of correct predictions divided by the total number of instances. Precision. This metric quantifies the model's ability to correctly identify positive instances true positives among all instances predicted as positive true positives false positives. Recall. Also known as sensitivity. This metric evaluates the model's ability to correctly identify all positive instances true positives among all actual positive instances true positives false negatives. F1 score. This metric combines precision and recall into a single value, providing a balanced measure of the model's performance. It's the harmonic mean of precision and recall. Visualization plots. Decision tree plot visualizes the structure of the decision trees, showing the decision nodes, branches, and leaf nodes. Feature importance plot displays the relative importance of each feature in the decision-making process. Features with higher importance contribute more significantly to the model's predictions. Fine-tune parameters. Nestimators. The number of trees in the forest increasing this value generally improves performance but can also increase training time. Criterion. The function to measure the quality of a split. Common options include Gini impurity and entropy information gain. Max depth. The maximum depth of each tree. Limiting the depth can prevent overfitting by reducing the complexity of the trees. Min-sample split. The minimum number of samples required to split an internal node. This parameter helps control the size and complexity of the trees. Min-samples leaf. The minimum number of samples required to be at a leaf node. Similar to min-sample split, it regulates the size of the trees. Max features. The number of features to consider when looking for the best split at each node. It can be an integer absolute number, a float proportion of features, or auto all features. Bootstrap, whether bootstrap samples are used when building trees. If true, each tree is built on a random subset of the training data. Promoting diversity. Uncertainty methods. Confidence scores. The model can provide confidence scores for each prediction, indicating the certainty of the classification. Higher confidence scores suggest stronger predictions. Out-of-bag OOB estimates. If Bootstrap is true, the model can generate OOB scores. These scores represent the average prediction error for each data point using trees that were not trained on that data point, providing a measure of prediction uncertainty. Challenges and fixes. Challenge 1. High variance due to the inherent randomness in the tree construction process. Extra trees classifier can exhibit high variance. This means the model's performance can fluctuate significantly when trained on different subsets of the data. Sample use case. When training an extra trees classifier on a dataset with a limited number of samples, the model's performance may vary greatly depending on the specific data points included in the training set. Fixes to challenge 1. Increase the number of trees. Estimators. A larger number of trees helps average out the variance across the ensemble, leading to more stable predictions. Adjust the max depth parameter. Limiting the maximum depth of the trees can help reduce the complexity and variance of the model. Utilize bootstrap sampling. Using bootstrap sampling introduces additional randomness in the training data, further reducing the risk of overfitting and high variance. Challenge 2. Feature importance interpretation. Interpreting feature importance scores from extra trees classifier can be challenging, especially when dealing with correlated features. Sample use case. If two features are highly correlated, extra trees classifier may attribute the importance of the prediction to one feature while the other remains seemingly unimportant, even if both are contributing equally. Fixes to challenge 2. Feature selection. Applying feature selection techniques beforehand can help identify and remove redundant or irrelevant features, making the interpretation of feature importance scores more reliable. Domain expertise. Utilizing domain knowledge can provide insights into the relationships between features and help interpret feature importance in the context of the specific problem. Permutation importance. Calculating permutation importance, which involves shuffling a single feature and observing the impact on model performance, can offer a more robust measure of feature importance. sklearn. Tree. Extra tree regressor. Description. Extra trees regressor is an ensemble learning method that combines multiple decision trees to improve prediction accuracy and reduce overfitting. It utilizes the extremely randomized trees algorithm, which introduces randomness at both feature selection and threshold selection during tree construction. This approach leads to more diverse and robust trees, effectively mitigating the impact of noisy data or outliers. Inputs. XA2D array representing the training data, where each row corresponds to a sample and each column represents a feature. YA1D array representing the target values for each training sample. Outputs. Predictions. The predicted values for new data points. Fitted model. A trained extra trees regressor object, which can be used to make predictions on unseen data. Steps. Tree construction. Multiple decision trees are constructed using the extremely randomized trees algorithm. For each tree, random subsets of features are selected at each node, and random thresholds are used for splitting the data. Aggregation. Predictions from individual trees are aggregated by averaging or voting, depending on the chosen strategy. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual values. R squared R2 represents the proportion of variance in the target variable that is explained by the model. Visualization plots. Decision tree visualization. Each individual tree can be visualized to understand the decision-making process. Feature importance plot shows the relative importance of each feature in the model's predictions. Fine-tune parameters. Estimates the number of trees in the ensemble. Increasing this value usually improves accuracy but can lead to longer training times. Max depth. The maximum depth of each individual tree. Limiting depth can help prevent overfitting. Min samples split. The minimum number of samples required to split an internal node. This parameter controls tree complexity. Random state. An integer for initializing the random number generator. Setting this value ensures reproducible results. Uncertainty methods. Bagging. The ensemble nature of extra trees regressor inherently introduces uncertainty in the predictions. Feature importance. The feature importance scores provide insights into the model's reliance on specific features. Challenges and fixes. Challenge 1. Overfitting to noisy or sparse data. Sample use case. Training a model on a dataset with a large number of irrelevant features or noisy data points. Fixes. Use a smaller number of estimators to reduce the complexity of the ensemble. Adjust the max depth parameter to limit the depth of individual trees. Consider using a data preprocessing technique, such as feature selection or dimensionality reduction, to remove irrelevant or noisy features. Challenge 2. Long training times for large datasets. Sample use case. Training a model on a very large dataset with a high number of features and samples. Fixes. Use a smaller number of estimators to reduce the computational cost. Consider using a parallel processing library to speed up the training process. Employ techniques such as early stopping or gradient boosting to reduce the number of training iterations. sklearn, tree, export graph viz. Description. The export graph viz function from sklearn, tree provides a way to visualize decision trees trained using scikit-learn. It generates a graph representation of the decision tree, which can be used to create visualizations and understand the decision-making process. Inputs. Decision tree. The trained decision tree model object from scikit-learn, such as decision tree classifier or decision tree regressor. This object contains all the information about the tree structure, including node splits, features used, and prediction outcomes. Output file optional. The path to the file where the graph viz representation of the tree will be saved. If not specified, the graph viz code will be printed to the console. Outputs. GraphViz code. The function generates a string containing the GraphViz.language code that represents the decision tree. This code can be used to visualize the tree using GraphViz or other tools that can interpret .language. Visualized tree optional if an output file is specified. The generated GraphViz code is saved to that file. You can then use GraphViz tools like Dot to generate a visualization of the tree in formats like PDF, PNG, or SVG. Steps. Tree traversal. The function traverses the decision tree structure, recursively visiting each node. Node information gathering for each node. It extracts relevant information, such as feature used for splitting if applicable, split threshold or value, class or value predicted at the node, sample count at the node, impurity measure e.g. Gini impurity for classification, GraphViz code generation based on the extracted information. The function constructs the GraphViz.code representing the tree structure. This code defines nodes, edges, and labels for each part of the tree. Metrics. Gini impurity for classification trees. The Gini impurity measures the randomness or uncertainty in the distribution of classes at a node. Lower Gini impurity indicates a more homogeneous node. Entropy, another impurity measure for classification. Entropy quantifies the disorder or randomness in the class distribution. Mean squared error MSE for regression trees. MSE measures the average squared difference between predicted values and actual values. Mean absolute error may similar to MSE but uses absolute differences, making it less sensitive to outliers. Visualization plots. Decision tree visualization. The generated GraphViz code can be used to create a visual representation of the tree, showing the splitting rules, features used, and predicted outcomes. Fine-tune parameters. Feature names. Providing the names of the features used in the tree can improve the readability of the visualization, making it easier to understand which features are driving the decisions. Class names for classification. Specifying the names of the classes can enhance visualization by making the labels clearer and more informative. Filled when set to true. The nodes in the visualization are colored based on their impurity or other metrics, providing visual cues about the homogeneity or randomness at each node. Rounded. This parameter determines whether the nodes in the visualization are displayed with rounded corners. Uncertainty methods. Confidence intervals for probabilistic models. Confidence intervals can be displayed on the nodes to indicate the uncertainty in the predictions. Prediction probabilities for classification models. Probabilities associated with each class can be visualized on the nodes, showing the likelihood of a particular class prediction. Challenges and fixes. Challenge 1. Overfitting. If the decision tree is too complex, it might overfit the training data, resulting in poor performance on unseen data. Sample use case. A decision tree with many nodes and deep levels, trained on a small dataset, might memorize the training data too well and fail to generalize to new data. Fixes to challenge 1. Pruning. Limit the depth of the tree. Minimum samples per leaf, or minimum samples per split to prevent overfitting. Regularization. Use techniques like L1 or L2 regularization to penalize complexity and encourage simpler trees. Cross-validation. Use cross-validation to evaluate the model's performance on unseen data and choose the best hyperparameters. Challenge 2. Difficult to interpret trees. Very large and complex decision trees can be challenging to interpret visually, making it difficult to understand the decision logic. Sample use case. A decision tree with hundreds of nodes and deep levels might be hard to interpret visually, even with a well-formatted visualization. Fixes to challenge 2. Simplification. Use techniques like pruning to reduce the size and complexity of the tree. Feature importance. Examine the feature importance scores provided by the model to identify the most influential features. Partial dependence plots. Use partial dependence plots to visualize the relationship between specific features and the prediction. SHAPS. Happily additive explanations. SHAP values provide a way to explain the contribution of each feature to the prediction. YAML. sklearn tree export text. Description. The export text function in scikit-learn's decision tree module allows you to visualize and understand the structure of a trained decision tree model in a human-readable text format. It provides a clear representation of the decision rules and branches within the tree. Inputs. Decision tree. An instance of a trained decision tree model. such as decision tree classifier or decision tree regressor. Feature names optional, a list of strings representing the names of the features used in the tree model. If provided, these names will be used in the output text instead of numerical indices. Outputs. Text representation, a string containing the text-based representation of the decision tree structure, including decision rules, feature names, and class labels or predicted values. Steps. Traversal. The function traverses the decision tree structure, starting from the root node and exploring all branches recursively. Rule extraction. For each node, the function extracts the decision rule that applies to that node. This rule is typically based on a specific feature and a threshold value. Text construction. The function constructs a text representation of the tree by combining decision rules, feature names, and class labels or predicted values into a hierarchical format. Output. The text representation of the tree is returned as a string. Metrics. Not directly applicable. The export text function is mainly for visualization and understanding a tree structure, rather than measuring its performance. Visualization plots. Text-based representation. The output of export text is a text representation of the tree, which can be displayed in a console or text editor. Fine-tune parameters. Not applicable. The export text function does not have any fine-tuning parameters. Uncertainty methods. Not applicable. The export text function is not directly related to uncertainty methods. Challenges and fixes. Challenge 1. Difficulty in understanding complex trees. Sample use case that resulted in challenge 1. A tree with a large number of nodes and intricate branching patterns can be challenging to comprehend visually. Fixes to challenge 1. Feature importance. Use the feature importances attribute of the tree model to identify the most influential features. Tree pruning. Prune the tree to reduce its complexity and make it easier to understand. Graph visualization. Use external libraries like GraphViz or Matplotlib to generate graphical visualizations of the tree, which can be more intuitive. Challenge 2. Long text output. Sample use case that resulted in challenge 2. Deep or wide trees can result in very long text output, making it cumbersome to read. Fixes to challenge 2. Feature selection. Reduce the number of features used in the model, which can simplify the tree structure. Tree pruning. Prune the tree to remove unnecessary branches and shorten the output. Text formatting. Use formatting techniques like indentation or line breaks to improve readability of the text output. YAML. sklearn. Tree. Plottree. Description. The Plottree function from scikit-learn's tree module is used to visualize decision trees. It provides a graphical representation of the decision tree structure, including nodes, branches, and leaf nodes. This visualization helps understand how the tree makes predictions based on the input features. Inputs. Decision tree. A fitted decision tree model created using decision tree classifier or decision tree regressor. Feature names. An optional list of feature names strings corresponding to the input features used to train the decision tree. This helps label the nodes and branches with meaningful feature names. If not provided, default numerical indices will be used. Class names. An optional list of class names strings for classification trees. This labels the leaf nodes with the predicted class labels. Filled. A Boolean value indicating whether to color the nodes of the tree. If set to true, the nodes will be filled with different colors based on the class or value they represent. Rounded. A Boolean value indicating whether to round the corners of the nodes. Precision. An integer specifying the number of decimal places to display for numerical values. Axe an optional matplotlib axis object where the tree will be plotted. If not provided, a new figure and axis will be created. Font size a floating point number specifying the font size for the text in the tree. Impurity a Boolean value indicating whether to display the impurity Gini impurity or entropy at each node. NodeIDs a Boolean value indicating whether to display the node IDs. Proportion a Boolean value indicating whether to display the proportion of samples that reach each node. Rotate a Boolean value indicating whether to rotate the tree. Feature names an optional list of feature names strings corresponding to the input features used to train the decision tree. If not provided, default numerical indices will be used. Class names an optional list of class names strings for classification trees. This labels the leaf nodes with the predicted class labels. Outputs. Visualization a graphical representation of the decision tree. Displayed using matplotlib. Axis object the matplotlib axis object containing the plotted tree. Steps. Initialization the plotTree function takes the fitted decision tree model as input and initializes the visualization process. Node placement the function determines the placement of the nodes in the visualization based on the tree's structure. Branch drawing branches are drawn connecting the nodes, representing the decision paths in the tree. Node labeling nodes are labeled with information such as the feature used for splitting, the threshold value, the impurity measure, and the predicted class or value. Visualization display the final visualization is displayed using matplotlib. Metrics. Gini impurity the Gini impurity measures the probability of misclassifying a randomly chosen sample from a node. Entropy is another measure of impurity, calculated based on the information gained from a split. Visualization plots. Decision tree visualization a graphical representation of the decision tree, showing the nodes, branches, and leaf nodes with labels. Fine-tune parameters. Filled controls whether the nodes are filled with color. Rounded determines whether the node corners are rounded. Precision specifies the decimal places for numerical values. Font size controls the font size for text. Impurity determines whether to display the impurity measure at each node. NodeIDs shows or hides the node IDs. Proportion controls the display of the sample proportion at each node. Rotate rotates the tree for better visualization. Feature names labels nodes and branches with feature names. Class names labels leaf nodes with class names. Uncertainty methods. Not applicable. Challenges and fixes. Challenge 1 overfitting when the tree is too complex. It can perfectly fit the training data but fail to generalize to unseen data. Sample use case that resulted in challenge 1 a decision tree trained with a high max depth value might overfit the training data. Fixes to challenge 1. Pruning using methods like max depth, minsamples split, and minsamples leaf to limit the tree's growth and prevent overfitting. Regularization employing techniques like CCP alpha to penalize complex trees. Challenge 2 unbalanced data if the dataset has an imbalanced class distribution. The tree might favor the majority class, leading to poor performance on the minority class. Sample use case that resulted in challenge 2 a classification tree trained on a dataset with 90 positive samples and 10 negative samples might primarily predict the positive class. Fixes to challenge 2. Class weights assigning weights to different classes to balance their impact on the trees. Training. Sampling techniques using techniques like oversampling the minority class or undersampling the majority class to balance the dataset. Cost-sensitive learning adjusting the cost of misclassification for different classes to prioritize accurate prediction on the minority class.